Okay, so as I said just a moment ago, we're going to understand limits. And in section 2.1, excuse me, 2.2, it starts off with something that looks like this. The limit as x approaches 6 from the negative side of f of x equals 7. So there's a lot going on there. Let me help you understand what that means. Limit as, so it's the limit as x approaches 6 from the negative side of f of x is 7. Now limits are a way of asking what's happening to the y coordinate when the x coordinate gets close to something. So what is happening to the y coordinate of a function? I'm not going to write that, but we're talking about functions. Maybe I should write it. Of a function as the value of x gets close to a particular number. So where's y going as x gets close to some particular number? Now, there's a little bit more in this notation than that, but I'll give you a second to copy this down. So what's happening to the y coordinate of a function as the value of x gets close to a particular number? That particular number is this right here. So in this example, it says x gets close to 6. Now there's two ways you can approach 6. You can approach 6 from the right or the left. You can get close to it in either direction. Now when you're approaching from the right, that's the positive side. When you're approaching from left, that's the negative side. So it comes from our coordinate axes, because if you're to draw a graph with 0 here, the positive side is to the right, the negative side is to the left. So I'll often say the limit from the left or the limit from the right, because we're talking about these limits. So as you approach 6 from the left, our function goes to 7. Okay. Now that gives you kind of an x and y coordinate pair. It's the point 6, 7. That's where the graph should get close to. So let's see that on a graph. In fact, on the handout, you should have this little graph right here. And all we have to do is draw in a function or draw on something that gets close to this point. So it doesn't really matter what you draw in particular. I'm just going to draw a straight arrow. Let's see. Try that again. So much for my straight arrow. Come on. All right, let's just try it this way. And we'll do a not so straight arrow. There. Where'd it go? I'm not sure what's going wrong with my tech here. Maybe I'll have to do it by hand. Or for those of you taking Spanish, con la mano. 6, 7, and 6, 4. So we're getting closer to this value of 6 on the x-axis. And we got to get close to the value of 7 on the y-axis. That's exactly what the limit there is telling us. The limit as x approaches 6 from the negative side of f of x is 7. So a function that would look like that has to eventually wind its way into that point. And that's it. That's what the graph would look like. Anything that winds its way into this point like that would be fine. Now, there's another side to this limit. That's the negative side. Let's look at the positive side. So the positive side, or the right, limit as x approaches 6 from the right of f of x is 4. So coming from the right, you've got a function that merges into this point. So let's just do something like that. And there's an example of a graph that satisfies both of these things. And that's all we're looking for in this first part of things. Give you a second to copy some of that down into your notes. Now you'll be doing the homework on WebAssign, and when you do things on WebAssign, a lot of times they have some multiple choice questions here for you. So let's take a look at what they would look on WebAssign and try and enhance our understanding of this a little bit. So on WebAssign, you'll get some choices and you'll be asked to explain what this means. And the correct explanation is, as x approaches 6 from the left, f of x approaches 7. As x approaches 6 from the right, f of x approaches 4. And it looks like that 4 got cut off a little bit. All right. So that explanation matches our graph. So are we good there? Move on to example B, or if there's something about this one that you're not sure of, let me know. It's easier for you to ask a question of me verbally. So if you got one, let me know. And okay. Let's continue to dive into limits. Move into example B, and share with you a little bit more about limits, talking about this one right here. In fact, these first three all wonderfully go together. So let's see about those. This is example B. Now, limits are what happens to the y value when a value of x gets close to some particular number. In this case, right here, for these first two examples, we're getting close to -3. So let me just put that point here on the x-axis, right there. So as you get close to -3, what's happening with the function? Well, for part A, am I getting close to -3 from the left or from the right?
The left.
Yeah, from the left. Thanks, Sarah. So getting close to -3 from the left, okay. So you're coming up this way. What y value am I getting close to? As I get close to, now you're not necessarily touching -3, you're just getting close to that. So what y value am I getting close to?
4.
Yeah, 4. So the limit as x approaches -3 from the left of f of x is 4. Perfect. Let's try part B here. limit as x approaches -3 from the positive side or the right of f of x. So what else? Your chance for 5 seconds of fame. What are we getting close to as we approach from the right?
-3.
As we approach -3 from the right, what's happening to the function? Where is it getting close to?
Oh, 4. Sorry.
Yeah, no worries. Thank you. Yeah, it's also getting close to 4. Now notice both of those two were the same. The limit from the left and the limit from the right actually match. And that allows us to do this. The limit as x approaches -3 of f of x is also 4. What's different about this as opposed to parts A and B?
It doesn't have a plus or a negative sign on the right.
Perfect. Thanks, Michelle. It doesn't have the plus or minus. Now, what this implies is that these two, the limit from the left and the limit from the right, they match. So this only exists if these two are the same. So this limit exists only if the two one-sided limits are the same. That is, they match. And they do. So in order for this limit to exist, these two have to exist and match. That's actually not true of our first problem. The very first problem we did here, example A, the limit from the left and the limit from the right were different. So backing up to part A here, if I did the limit as x approaches 6 of f of x, the answer would be D and E. Does not exist. Because the limit from the left and the limit from the right are different. The only time that this one's going to exist is if these two are the same, like it did in example C here. Well, example is A and B are the ones that matched. Are we okay with that? That's an important part here, so I don't mind pausing for a second if you have some follow-up on that.
So how do you know it does not exist when it approaches from, I think you said the right?
Good question. Good question. So it doesn't exist if the limit from the left and the limit from the right are different. So these two numbers aren't the same. The limit from the left and the limit from the right are different. They're going to different points. So that's why this one didn't exist. These two are the
That
same.
makes sense.
And if those two are the same, then this one exists.
Okay, thank you.
Yeah, appreciate it, Sarah. Now, interestingly enough, let's take a look at f of -3. What's the value of the function at -3? Does anyone know what this little hole notation means?
There is none.
Yeah, it's
Not a point.
undefined. Exactly, thank you. So it's undefined. And that's something that's a little bit strange for us, is that sometimes the limit could exist even though the function is not defined. And it's a little unsettling. And I get it. I remember being a calc student myself going, wait a minute, really? But it's you know, it's the way it is. Now, if this function actually was defined, then it could be a continuous function if it had f of -3 was 4. But right now, it's undefined. Let's keep working with this unless there's some more comments or thoughts on these first four here. Okay. Mhm. Let's jump down to part G here. How come it's not letting me get down? All right. Well, part G's looking at the limit as x approaches 0. Now, I kind of like this because it's making us think about what we just looked at. So let me write this down here. G, limit as x approaches 0 of h of x. Now, in order for this limit to exist, there's two other limits that we need to look at. We need to look at the limit as x approaches 0 from the left of h of x, and the limit as x approaches 0 from the right of h of x. So let's see if we can't look at those two, because in order for this one to exist, these two have to be the same. So let's look back at the graph. So as we approach x equals 0, put that right there. As you approach x equals 0 from the left, what's the function going to? What y coordinates is it going to?
1.
1.
Yeah, it's going to 1. How about as we approach from the right?
-1.
-1.
Yeah, thank you, -1. So we got 1 and -1 for those two. What's that say about this limit overall?
Doesn't exist.
Yeah, thanks, Cole. Does not exist. Oh, can't happen. Oddly enough, in this one, h of 0 is actually defined. What's the value of h of 0?
1.
Yeah, 1. The function is defined at 1 here. Notice you got a closed circle here and an open circle down here at -1. So the closed circle is the value of the function at that point. So h of 0 is 1. Now there's a couple last ones let me finish up with here. And the next one I want to look at is part I. Let me pause for a second, see if you want to try and tackle part I. Limit as h approaches, excuse me, as x approaches 2 of h of x. So I'll pause for a second while you work on that one. So in order to consider this limit, even if you don't write this down, what you have to be looking at is both of these, the limit from the left, the limit from the right. And in this case, both of those are going to the same place. Both of those are going towards this point here at 2 and 2. So the limit from the left is 2. The limit from the right is 2. And only when both of these exist and are equal can you fill in that one. Say, all right, the limit is 2. Now, it doesn't matter exactly if the function is defined here or not. In fact, h of 2 is undefined. That's okay. Its limits still exist. And that's the important part. Let's actually look at a graph for one. And we'll look at this one. So sketch the graph of the function and use it to determine the values of which values of a for which the limit exists. The limit is going to exist as long as you have a nice continuous function. And we'll define that more rigorously later. That's just going to mean that you can draw the graph without lifting your pen from the paper. And if that's true, your limit's going to exist. me see if I can help you out though with the graphs in this one. Let's see. Yeah, I'll put a link in the chat here for you. You'll find that we're going to use Desmos an awful lot. I'll also use the graphing calculator, show you a lot about that. But what's convenient about Desmos is I can quickly give you these kind of graphs. So in particular, what we have in problem number 12 is what's called a piecewise graph. So it's f of x is one of these three things. It's the cube root of x for x less than -1. It's x for -1 less than or equal to x less than or equal to 2. And it's x minus 1 squared for x greater than 2. So this function here, we want to know where its limit's going to exist. Basically, where it's continuous is where it's going to amount to. Here's your function. It's the cube root function. Now, if I got rid of this little part right here, then I get the entire graph of the cube root. But I only want the cube root for values of x less than -1. So let's restrict that. Likewise, we want to graph the value or graph the function y equals x for values of x between -1 and 2. So it's going to look like that middle piece. And then we have this piece right here, which is going to be a parabola. We're only going to get part of that graph as well. So it's probably easier to list the values for which a limit's not going to exist or for which the function is not continuous. Our limit's going to exist everywhere the function is continuous. But there's one point where the function is not continuous. What's that point?
2.
2. Yeah. So the function is not continuous at x equal 2. You see what's going to happen here is you have this jump discontinuity. We'll talk more about it later, but the answer to the question here is x equal 2. So actually, let's just look back at how they phrase the question. Determine the values of a for which the limit exists. So your limit's going to exist for all values except x equal 2. Limit exists for all values of a except a equal 2. At that point, you've got problems. Let's look at another one, and we're going to do this next one with our calculators. So let me help you out with that. So the next one is going to be problem, it's label number problem number 22 on your handout. Looks like this. This is going back to the work that we did in section 2.1, a different way to try and get at limits. Instead of doing it visually with a graph, we're going to do it numerically. We're just going to look at a table of values and decide, okay, what does it look like it's getting close to? So if you got a graphing calculator, you might want to take it out now. There's a good place to look at it. And let me share with you mine here. And maybe I should start from scratch. So let me hit a couple clear buttons. And you can follow along with the keystrokes that I use down here in the key history. So looking back at our function, I want to type that one in. I'm going to use an X as opposed to an H, just because it's going to be absolutely convenient. So let's see here. I'm going to hit the Y equals key. Now there's a couple ways you can put this in. Kind of depends on how up to date your calculator is, if you want to get fancy or not. It's up to you. The first one we'll do is kind of like a basic way that'll work with all the calculators. So I need 2 left parentheses. One is for the entire numerator. The other one is just for that binomial. I want 2 plus x, and then a right parenthesis, raised to the 5th power. So that's that character up here, raised to the 5th power. Now, depending on your calculator, if you have one like mine, you're gonna need to exit the exponent, so just hit the right arrow. If you got an older calculator or one that's not doing the math print here, then you won't have to do that. It'll just be an up arrow and then a 5. Minus 32. Now that second right parenthesis closes off the numerator. And then we'll divide that by x. If you want to get a little fancier, that's kind of cool. Let me show you a little trick on your graphing calculator. Again, this is for calculators that have an up-to-date operating system. If you hit the alpha key, then the y equals key. Then the first option here allows you to do fractions more or less the way you would write them on your paper. So I'll just choose that by pressing the number 1 or hitting enter. And now I can enter this just as a regular fraction. It'd be parentheses 2 plus x, parentheses raised to the 5th, minus 32, divided by x. So it's nice. What I like about that is that it's less complicated in terms of parentheses, but not everyone could do it that way. So whatever. Regardless of which way you put that in, one thing that I want you to do is make a settings change to your table setups. So follow me here. Hit the second key, then the Windows key, and scroll down to this third line down here and set independent to ask. So scroll down a couple, go over here to ask and press enter if it's not already highlighted in black. Dependent should be set to auto. What this is going to do is it's going to allow you to type in whatever values of x that you want when you create your tables, and that's a good thing. Leave it set here for the rest of your life, or at least the rest of this course, whichever comes first. Now, when you're done with your table setup, hit second, and then the graph key, that'll take you to the table. If there's some other values there, you just hit the delete key. Now, the reason I'm getting 2 of these things here is because I entered it twice. You may only get 1 because you entered it once. And now let's type in the values of x that they're looking for. They want a sequence of values of x that get close to, but not quite touch, 0. So we're going to do a symmetric set of points, going from 0.5 to 0.1 to 0.01, 0.01, etc. And then we'll do the opposites of those, do the negative values. So I'll start out with 0.5, 0.1, 0.01, 0.001, and I think I gotta go one more, 0.0001. And your calculator here is resorting to scientific notation. It's 1e negative 4, so that's got 3 leading exponents, or 3 leading zeros. So this is approaching 0 from the right, getting closer and closer to 0 from the right. How about from the left? From the left, we're just going to use these same values except negative. So negative 0.0001 and negative 0.001 and so on. Negative 0.1, oops, I didn't hit the enter key on that one, so let me type that in again. 0.01, negative 0.1, and negative 0.5. What you should see here, though, should convince you of what the limit is. As we approach x equals 0 from the left or from the right, what value of x am I getting close to?
80.
80.
Yeah, it looks like you're getting closer to 80, right? Yeah, that'd be my guess. So 80 is the conjecture that we have for the limit. That'd be your answer. So the limit as x approaches 0 of this function to this quotient is 80. Just write that down. But are you seeing how the values, the decimal values for y are closing in on that particular value of 80? Let me get back here to, there we go. These values here and in this column are getting closer and closer to 80 as you get closer and closer to 0 along the x-axis. And these values are really close to 0. We're within a 10,000. Okay. So we'll finish up this section with problem number 16, at least problem 16 from the written or handheld version of the book. And it gives us a couple things. They want us to fill in a plausible graph. But personally, I would start out with these two pieces of information here. For instance, f of 0 equals 6. So this is telling you you've got a value of 6 as a y-intercept. And then f of 8 equals negative 1. So let's put that point on our graph. Let's see about answering some of these other ones or drawing something that matches some of these other conditions. So f of 8 equals negative 1. That would be about there. Oops. Let's see about matching some of these other things on our graph. So the limit as x approaches 0 of f of x equals 4. So, what's that saying? Well, that's saying as you get close to 0 from either direction, you're getting close to the value of 4. So let's draw something that matches that. And I'll use blue for that. Now I've drawn somewhat of a straight line here. And this one, maybe I'm not going to draw such a straight line. Something like that. But both of these are heading to the point 0 and 4. So you have a limit as x approaches 0 of f of x equals 4. And interestingly enough, the value of here is not defined, is it? The value of f of 0 isn't 4. Even though the limit is 4, you're getting close to a hollow point. The value of the function there is 6. That's okay. What it means is that the function isn't continuous at 0, but it does have a limit of 0. So that's the first part here. Let's try the second part. So for the second part, the limit as x approaches 8 from the left of f of x is 1. So what that means is that as we're approaching 8 from one of these sides, we're getting close to 1. Now, I wish I could do a hollow dot a little bit better, but I didn't. That's okay. From which direction am I getting close to this? The left or the right? What is that notation telling me?
Is it from the left because it's coming from the negative side?
Thank you, Alejandra. Yeah, it's coming from the negative side, so it would be from the left. So there's your limit there. Probably shouldn't be drawing the arrows, that's okay. But as you approach x equal 8 from the left, you're getting closer and closer to 1. Situation changes when you approach from the right. When you approach from the right, we're going to get closer and closer to -3. So let's find -3. That's going to be down around here. As we're approaching -3, so we're getting closer to that point there. Let me just clean that up a little bit. That didn't look too good. So you're getting closer and closer to -3 as you approach from the left. It doesn't even matter exactly how you get there. You're eventually going to get there. Now, what's that say about the limit overall? If I were to add a little bit to this problem, it'd probably be what's the limit as x approaches 8 of f of x? So it'd be this question right here. That would be a good follow-up to those previous two. The limit as x approaches 8 of f of x. Now notice this time it's not a one-sided limit like these other two. This one is just, well, what's happening to the function as x approaches 8? Or maybe you want to look at things up here. Underlined in yellow and underlined in purple. What's happening with it?
Is it undefined because they're not the same?
Excellent. So
Or, yeah.
this limit does not exist because the limit from the left and the limit from the right are different. Thank you, Alejandra. Nice. That's a nice way to end things up for section 2.2. Any other thoughts or comments on this one?
Wait, but doesn't like it have a value though at f of x?
It does.
Right.
It does. But that still doesn't change the limit.
Right.
The limit is what's happening as you get close to x equal 8. And because the limit from the left and the limit from the right are different, the limit doesn't exist. But you're right. F of 8 itself was what? -1, I think. So yeah, this is kind of a strange case where the limit doesn't exist, but the value of the function is defined. Well, those kind of things happen.
Thank you.
Could
Thank
you
you.
explain like the difference between does not exist and undefined?
It's not a huge difference. But in order for a limit to exist, the limit from the left and the limit from the right have to be equal. If that's not true, then the limit is said not to exist. Undefined just means that there's a hole in your graph, that the value of the function is just not said. Now this one, let's see, maybe I want to go back up to this example right here. So for example B, at x equal -3, right up here, notice there's a hole in the graph. Likewise, there's a hole in the graph here. That hole means the function's not defined at that point. So, okay, the function is not defined. That's all you can say about it. Whereas at x equals 0, the function is not defined here, but it is defined up here. So the value of the function is defined at 0, where it's not defined at -3 or 2. It's not something all that formal that I would worry myself about. I just use different terms for the two. It's just out of some habit. If it has some formal definition about it that I'm not aware of, I'll let you know, I'll look into it, but I think it's just the way we refer to those as doesn't exist and undefined.
Okay, thank you.
Yeah, appreciate it. Thank you, Marley. Anything else?
I have a question.
Yeah,
Yeah, I have a question. Okay, so can you go back to the other graph, please?
sure.
The one where all the other functions were.
These,
Okay, so yeah, those. So for the second limit, the one where f of x equals 1, I guess I was kind of confused with the graphing on it because so if it's,
yeah, you're
because
right.
shouldn't it be on the left, shouldn't it be on the left-hand side if it's coming from the negative side, approaching 1 on the
well, there is-
y-axis?
There is a mistake here, and I wasn't looking at my graph too carefully. Coming from the left, it should get down to 1. I was just regarding this line as a 1. It's actually a 2 there, but coming from the left, it's getting closer to 1. But
So would you still not draw it on the left-hand side, coming from the left-hand side though, the limit?
this is the left-hand side, right? So we're to the left of this point. I'm not sure I'm answering your question or seeing what the confusion is.
No, you know what, I'm thinking about it backwards, like coming from the negative hand side. So I would have drawn it literally coming from -8 on
Oh,
the second quadrant,
okay.
first quadrant, or yeah.
So, yeah, so the negative is just referring to the fact that it's coming from the left.
Yes,
That's all. And then this is coming from the right, so that'd be from the positive side, and this is from the negative side. So,
yeah, okay, I got the clarification, thank you.
all right, thank you. All right, that'll put a wrap on it for section 2.2.